Hi and welcome to video 6 of the integration video series for 2-unit mathematics. This one we're going to look at the area enclosed by the y-axis this time, not the area enclosed by the x-axis. So let's have a look at a good example. This example here will illustrate it quite nicely. We've got to find the area enclosed by the curve y equals x squared, which is your normal standard parabola. The area enclosed by the curve and the lines y equals 0 and x equals 0 in the first quadrant. So what that looks like on a graph, we've got to find the area between the curve and the y-axis really, which is this bit in here. Excellent drawing. So that area in there is what we're trying to find. In the other question so far, we've found the area under the curve between the curve and the x-axis. This time it's the y-axis. So this sums up our first good move to make x the subject of our function. Instead of y equals, we want x equals. So we'll take this and from y equals x squared, we should really get, so when we square root something that's had a square happening to it, if we square rooted both sides, we'd actually get plus or minus square root of y equaling x. But because the question says it's in the first quadrant only that we're considering, we can actually override that and just ignore the minus section of that. And so that will then translate into x equals root y. And just to make it a little bit easier to work with, we're going to call it x equals y to the power of a half. So that's going to be the function we're going to be working with here. Alrighty, so our area between the y equals x squared curve, the black parabola there, and our y-axis can be found by the following setup. Our area equals our integral between 0 and 4. In this case, it's actually y values of 0 and 4 of our expression y to the power of a half, and interestingly it's got a dy at the end where we're integrating with respect to y instead of usually we integrate with respect of x. Okay, so to integrate that, we add 1 to the power and divide by the new power. So that'll equal when we add 1 to the power, we get y to the 3 over 2. And then we divide by that new power of 3 over 2 between the x values of 4 and 0. And when we're dividing by a fraction, we multiply by the reciprocal. So that turns out to be 2y to the 3 over 2 over 3 when we turn the bottom upside down and multiply between 4 and 0. Now perhaps we better put that index version there into normal language to help our brain a little bit here. So it's 2 times, the 2 on the bottom of the indice there means to root, and we've got y cubed over 3 between 4 and 0. Now that allows us to sub 4 in to our expression and sub 0 in and subtract those two. So I'll just bring this up to the top here, and we'll start our second column of working here, run out of space a little bit. So if I sub 4 in wherever there's a y, I'll have 2 square root of 4 cubed over 3. And I'm going to subtract 0 subbed in there, 2 root 0 cubed over 3. And my final answer there should be 5 1/3 units squared. They're square units because we're trying to find the area between the curve and the y-axis. Probably the most important part of the whole thing, because we're going to find the area between the curve and the y-axis this time, this is the key bit, to make x the subject of the formula before we even start. And then the rest of it follows pretty much like the other questions we've done. But we must make that change to get an expression of x equals before we start processing. So that's our good example. I hope that illustrates a lot of what you need for the exercise. Thanks a lot for listening. Bye.